10 billion light-years away, there is a lighthouse in the dark that should not be able to exist. Its light is so intense it washes out the galaxy that hosts it, like a floodlight aimed straight at the universe. At the center sits a black hole so huge that when astronomers first tried to weigh it, they kept redoing the math, convinced they had made a mistake. But the mistake never appeared. The number stayed. And the closer you look, the stranger it gets, because this thing was already enormous when the universe was young. Stay with me for this one, and if you enjoy deep dives like this, like and subscribe. We are used to black holes as villains in a neat little story. A star collapses, a dark object remains, and anything that wanders too close disappears. That version is not wrong, it is just small. It is the black hole story written at human scale. Out there, the universe writes a bigger version. The object we are chasing has a name that looks like it belongs on a filing cabinet label, not a cosmic horror. TON 618. It was first noticed as a tiny point of light among countless other points of light, the kind of thing you could easily dismiss as just another distant quasar. But once astronomers realized what it was, it stopped being a dot and started being a question. How can the universe build a black hole with a mass of about 66 billion suns? Not 66 billion stars in a cluster. 66 billion suns worth of mass packed into one gravitational well. If we placed that black hole where our sun sits, the size of its event horizon would reach far beyond the orbits we instinctively think of as the edge of home. It would stretch past the familiar planets, past the cold frontier, out into a distance that makes the solar system feel like a small neighborhood. The idea is hard to hold in your head because your brain keeps trying to treat the black hole like a point. But the event horizon is not a point. It is a boundary in space, a surface you can cross. And for a black hole like this, that boundary would swallow the scale you grew up with. So why have you never heard of it the way you have heard of the one at the center of the Milky Way? Part of the answer is that it is very far away, about 10 billion light-years. That number is already a story in itself because it means the light we detect began its journey long before anything like us existed to see it. When that light left its home galaxy, Earth did not exist yet. The sun had not formed yet. The universe was younger, denser, and far more violent than it is now, and yet that ancient light still reaches us. It reaches us as a quasar, one of the brightest phenomena in the cosmos, powered not by fusion like a star, but by gravity itself. A quasar is what happens when a supermassive black hole is not quietly sitting at the center of a galaxy, but actively feeding. Gas and dust spiral inward, heat up, and radiate an enormous amount of energy before vanishing across the horizon. For TON 618, that feeding process becomes a kind of cosmic spotlight. The luminosity is staggering, on the order of 140 trillion suns, not because the black hole itself shines, but because the space around it is being forced to glow. Right here, the paradox tightens. A black hole is supposed to be dark. TON 618 announces itself by being too bright to ignore. That brightness is not just spectacle, it is a clue. It tells us there is a huge reservoir of matter falling inward, and that the physics of that fall is converting mass into radiation with frightening efficiency. It also tells us something else that feels almost emotional when you sit with it. This is not a relic, this is not a fossil, at least not in the moment we are seeing. It is alive in the only sense that matters in astrophysics. It is doing work, it is changing its environment. Now if you are thinking, okay, but how do we know any of this? That instinct is perfect. Skepticism is the seatbelt of curiosity, because we cannot fly there. We cannot point a ruler at it. We cannot watch stars orbit it the way we can for the black hole in our own galaxy. We are looking across an ocean of time and emptiness and trying to weigh something that cannot be seen directly. So we do what astronomy always does when the universe refuses to cooperate. We become detectives. We look at the light. We look at how it flickers. We look at the fingerprints inside it, the spectral lines, the way gas moves under gravity, the way regions of glowing matter respond to changes in brightness. We build a chain of inference so tight that if the conclusion is wrong, the universe would have to rewrite multiple independent clues at once. That is why TON 618 is not a rumour. It is not a viral factoid. It is an object that emerged from patient measurement, from repeated checks, from methods that have been tested on nearer systems where we can verify them. Still, there is something psychologically unfair about it. Your mind wants a villain you can picture, a mouth in the dark, a swirling drain. But TON 618 is both more ordinary and more unsettling than that. Ordinary, because it follows the same basic rules as every other black hole. Gravity pulls, matter falls, energy radiates. Unsettling, because the scale is so far beyond your instincts that every normal sentence sounds like a lie. 10 billion light years, 66 billion solar masses, a quasar glow that can outshine entire galaxies. It is too much. That is the point. It is a stress test for nature. And here is the deeper reason this story matters. TON 618 is not just a record holder, not just the biggest thing in a cosmic trophy case. It is a clue about what the early universe was capable of, how fast structures could grow, how violently galaxies could feed their central engines, and where the true limits might be for black holes themselves. When you find an extreme object, you do not just learn about the object. You learn about the rules that allowed it, and the rules that tried, and maybe failed, to stop it. So in this series, we are going to do something a little strange together. We are going to take TON 618 seriously as a place, even though it is unimaginably distant. We are going to treat its light as a message from a younger universe, and we are going to chase the logic from the photons that hit our telescopes all the way down to the edge of the horizon, where the meaning of words like inside and outside start to wobble. Because once you accept that something like this exists, you cannot unsee the implication. If the universe can build one monster like this, it can build others, and the only reason you are not surrounded by them is that the universe is bigger and stranger than your everyday sense of reality can keep up with. Now let us start moving outward from home, because before we can truly face TON 618, we have to feel what 10 billion light years actually means. Close your eyes for a second and picture home. Not the planet yet, just the room you're in, the chair or bed under you, the faint hum of whatever device you're watching this on. Your body feels like the center of the scene, because that is how your brain is wired. You are built to anchor reality around yourself. Now pull back. You're on a spinning sphere of rock and metal wrapped in a thin film of air, orbiting a star that you almost never see as anything except a bright circle in the sky. At this scale, Earth feels huge. Continents, oceans, weather systems. Yet if we zoom out just a little more, that feeling collapses. The solar system is mostly nothing. The planets are specks separated by deserts of vacuum. And even that is only step one. Imagine leaving Earth the way a spacecraft does. First, you punch out through the atmosphere. The blue fades to black. The sun becomes painful to look at. You pass the moon, a week-long journey suddenly compressed into a thought. The inner planets line up as tiny moving lights. Mars, then the asteroid belt, then the gas giants with their ring systems and moons. Finally, the realm of comets and ice, where the sun is no longer a blazing disk but a bright star among many. From far enough away, the solar system is a dim bubble, where almost all the mass sits in a dot you could cover with a pinhead, and almost all the volume is empty. Even the word empty is misleading. There are particles here, stray atoms, a thin wind of charged particles, but compared to anything your senses evolved for, it is absence. Keep going. Now the Milky Way begins to take shape. Our galaxy is a disk of hundreds of billions of stars, tens of thousands of light years across. It has spiral arms, a central bulge, a diffuse halo. When you see artistic renditions of it, it looks dense, like a glittering city of lights. The truth is more lonely. On average, stars are separated by light years of separation. You could fly for generations between them and never see more than distant points. When we talk about distance inside a galaxy, we are already in a world where words like walk or drive or even fly have stopped making sense. Light itself, the fastest thing the universe allows, takes years to cross the spaces between ordinary stars. Our entire technological history has not lasted long enough for light to complete a single lap around the galaxy, and TON 618 is still unimaginably far beyond that. We pull back again, and the Milky Way shrinks to a smudge. You notice it has company. Andromeda, our larger neighbour, drifting toward us. Dozens of smaller galaxies orbiting like satellites. Together they form the local group, a tiny gathering compared to the larger structures it belongs to. Beyond that, more groups and clusters. The Virgo cluster, the Coma cluster, a loose association of structures tied together by gravity into a vast supercluster. At this point, the picture changes in your mind. You're no longer looking at individual galaxies one by one. You're seeing patterns, filaments and walls made of galaxies, stretching across hundreds of millions of light years. Between them are voids, gigantic regions with almost no galaxies at all. The universe starts to look like a three-dimensional web. Where the threads meet, you find clusters. Along the threads, you find chains. In the gaps, you find silence. This is the cosmic web. What we call empty space is no longer a backdrop. It is part of the architecture. Gravity has pulled matter into these long strands, leaving in between them cavernous voids where there is almost nothing to see. If you could somehow sit inside one of those voids and look around with perfect eyes, the universe would appear as a faint, distant lattice in all directions, with you floating in the middle of almost pure darkness. Here is the key shift. When we say TON 618 is about 10 billion light-years away, we're not saying it is just far off along a flat map. We're saying it lives in this three-dimensional web on one of these filaments, in a specific environment of clustered galaxies and flowing gas. The light we see from it has threaded its way through billions of years of cosmic history, past countless structures, through regions of different density, all while the fabric of space itself has stretched. You might be wondering how meaningful distance even is in a universe where space expands. 10 billion light-years sounds like a simple thing, but it hides complications. The light from TON 618 has been travelling toward us for roughly 10 billion years of cosmic time. During that journey, the universe has expanded so much that the present-day distance between us and the quasar is now far larger than the distance the light originally had to cross. When we quote a distance, we are really choosing a way to talk about several related but different concepts at once. That is another reason this object feels like a test of our intuition. Your brain wants space to be a fixed stage, a place where you can lay a ruler down and trust it. But on the scale of billions of light years, the stage itself moves. Space stretches. Galaxies ride along like passengers on the current. Light does not take a simple straight path through an unchanging arena. It travels through an evolving medium, and what was near when the light began its journey is not necessarily near now. Yet in a strange way, that makes the connection more intimate. When you look up at the night sky, you are not seeing a present tense universe. You are looking into time. Nearby stars are old snapshots. Distant galaxies are ancient photographs. A quasar 10 billion light years away shows you the universe as it was when it was less than half its current age. The further you look, the younger the universe appears. Your telescope becomes a time machine, and the cosmic web becomes a kind of fossil record. So leaving home is not just about moving outward in space, it is about moving backward in time. As we conceptually travel from Earth to the realm of TON 618, we're also travelling from a mature universe filled with large settled structures into a wilder era when everything was more compressed, more energetic, more hungry. Galaxies were forming stars at furious rates. Gas was falling into potential wells carved by dark matter. Black holes were feeding more actively. Quasars were common. TON 618 lives in that epoch. From our perspective, sitting here in a quieter, older cosmos, it is like seeing a single blaze left over from a season of wildfires, frozen in time and projected into our sky. That is part of why it feels eerie. The light is new to us. The events are long over. The quasar we see may have already dimmed or transformed beyond recognition, while its ancient glow is only now washing over Earth. At last, you can start to feel what 10 billion light-years means. It is not just a long road, it is an entire difference in reality. The scale of the cosmic web, the near emptiness between galaxies, the expansion of space, the time delay between cause and sight, all of that is baked into that one number. And somewhere along one of those distant filaments, in a galaxy we can barely resolve, sits the engine we're chasing. No longer just a line in a catalogue, but a real place in a mapped web of matter. A destination with an address in the universe. Now that we have pulled back far enough to feel the stage, it is time to walk up to the monster itself and see what those impossible numbers really imply. From the distance of 10 billion light-years, TON 618 is just a point. On a detector in a telescope, it is a spike in brightness, a dot that looks no different from thousands of other dots. If you did not know better, you would scroll past it in a catalogue as just another quasar. But now that we have followed the trail of the cosmic web down to this one object, we can no longer afford to see it as a dot. We have to do the uncomfortable thing and turn that dot back into a three-dimensional place. The first thing we meet is not the black hole itself, but its disguise. TON 618 blazes as a quasar, a kind of cosmic searchlight powered by a feeding black hole. The core of its host galaxy is so bright that the rest of the galaxy vanishes in the glare. Gas, dust, and perhaps shredded stars are swirling inward in a vast disk. Friction and magnetic turbulence heat that material to extreme temperatures. Before it loses the battle with gravity and crosses the point of no return, it radiates with a power that outshines entire galaxies. In the case of TON 618, the total light output is roughly 140 trillion times that of the Sun. That number is irritating at first. Your brain hears it and shrugs. Trillion is a word that lost its bite in an age of giant budgets and data storage. So instead, imagine this. If you replaced our Sun with a quasar like TON 618, the sky would not just be brighter. The night side of Earth would be burned away. The oceans would boil. The atmosphere would be stripped. It would be like parking next to a continuous wall of nuclear explosions, forever. And then we remember that this light is only the side effect. At the heart of that glare sits the thing doing the pulling, a black hole with a mass of about 66 billion suns. A solar mass is the mass of our Sun, a ball of hydrogen and helium big enough to anchor the orbits of all 8 planets and everything else in the solar system. Multiply that mass by 66 billion, and you have the gravity well at the centre of TON 618. We need a comparison to feel what that means. The black hole at the centre of the Milky Way, Sagittarius a star, weighs in at about 4 million solar masses. For years that felt huge. It anchors the rotation of our entire galaxy. Yet TON 618 laughs at that. This ultramassive black hole is roughly 15 to 20,000 times more massive than the giant in our own backyard. If you tried to represent the mass of Sagittarius A star as a single grain of sand, TON 618 would be a rock the size of a small house. Mass in a black hole also sets the size of the event horizon, the boundary beyond which nothing can escape. The more mass you add, the larger that dark sphere becomes. For a black hole of one solar mass, the event horizon radius would be a few kilometers. For TON 618, using the same relationship, the radius comes out to almost 200 billion kilometers. That is the distance from the center to the edge. The full diameter would be close to 400 billion kilometers. Those numbers are as empty as they are large until we anchor them. Place TON 618 where our Sun is now. The event horizon would form a black sphere centered on the middle of the solar system. The orbit of Mercury would be gone, swallowed many times over. Venus, Earth, and Mars would be forgotten, with room to spare. Jupiter and Saturn would sit well inside the horizon. Uranus and Neptune would vanish without ever approaching the edge. Even Pluto, running on its distant elongated path, would be deep inside the region from which light cannot escape. The surface of no return would lie more than 30 times farther out than Pluto ever travels. In other words, the entire solar system would fit comfortably inside the event horizon of this one object, with enormous empty margins. That last phrase is important: empty margins. When we imagine a black hole, it is tempting to picture it as a solid ball of something, a hard sphere made of compressed matter. The physics is stranger. The event horizon is not a surface made of material. It is a boundary in space-time, a place where the paths that light could possibly take all curve inward. Inside that radius, every direction forward in time leads deeper into the gravity well. Outside, there are still pathways that allow escape. So when we say the solar system could fit inside TON 618, we're not saying the black hole is a giant solid object that would crush the planets by taking up space. We are saying that the region of no escape around it would be that large. The actual matter that collapsed to form it may occupy a region much smaller than the horizon suggests. In classical general relativity, the mass is said to be concentrated at a singularity, a point where the equations break down. Here comes another twist that wrong-foots intuition. For a black hole of stellar mass, the gravitational tides near the event horizon are catastrophic. The difference in pull between your head and your feet would be so intense that you would be torn apart before you even crossed the boundary. For an ultramassive black hole like TON 618, the horizon is so far from the center that the gradient of gravity there can be surprisingly gentle. The same gravity well that dominates entire galaxies can feel locally calm at its edge. If you could somehow remain intact in the environment around the accretion disk and jets, and you drifted toward the horizon of TON 618, you might cross the boundary without feeling a sharp jolt. No sudden wall, no crunch, just a line in space that you only know you passed because your options for where to go next have quietly collapsed to one direction, inward. This contrast makes the numbers more unsettling. On scales your body understands, mass and size go together. A heavier rock is usually a bigger rock. With black holes, especially ultramassive ones, the relationship between mass, size, and experience becomes slippery. The event horizon gets bigger with mass. The average density inside that horizon, if you try to define such a thing, actually drops. The tides at the horizon get weaker, yet the total grip on the surrounding universe gets stronger. TON 618 is an extreme example of this misalignment between intuition and reality. Its mass is ridiculous. Its event horizon could swallow star systems. Its light output screams across billions of light years. And yet, the place where its most defining line sits, the horizon itself, could feel deceptively ordinary in the moment of crossing. At this point, a natural suspicion bubbles up. How sure can we be about any of this? We have never flown a probe out there. We have not resolved the black hole directly as a disk on the sky. All of these statements about radius, mass, and light output are the result of calculations and models. Should we trust them? The honest answer is that each individual step involves assumptions and margins of error, but they are not guesses thrown in the air. They are the extension of methods tested closer to home. We know how gravity behaves around smaller black holes and compact objects. We know how gas emits light when heated to certain temperatures. We know how spectral lines broaden when gas moves at high speeds in deep gravitational wells. We know how bright an object must be to produce the flux we see at a given distance. When those independent pieces are put together for TON 618, they all point toward the same uncomfortable picture. An ultramassive black hole in the 60 billion solar mass range, in a galaxy far away, in a universe much younger than today. We will later peel apart how those measurements are made and how we weigh something we cannot touch. For now, it is enough to sit with the geometry. A point of light on a sensor that hides a dark sphere large enough to erase our entire solar system, embedded in a feeding disk that shines with hundreds of trillions of suns. Once you feel those numbers, TON 618 stops being an entry in a catalogue and becomes what it really is. A challenge thrown down by the universe. A test of whether our theories of gravity, light, and cosmic history can handle the largest monsters they predict. The next step is to look past the numbers and ask how such a colossal engine actually works, and why it shines so brightly while trying to swallow everything around it. We keep talking about TON 618 as if the black hole itself were shining. That is the first lie your brain tells you. The black hole remains what it always is, a region from which no light escapes. The glare that reaches us, the one that outshines galaxies, comes from the stuff that has the terrible luck of not being inside yet. To understand the real engine here, we have to hover just outside the point of no return and watch what happens to anything that wanders too close. Gravity does not simply pull things straight in. Almost nothing in the universe aims perfectly at a target. Gas clouds, stars, and stray debris carry sideways motion as they fall. When that material approaches the black hole of TON 618, its sideways motion is enough to keep it from plunging straight down. Instead, it settles into a spinning structure, a flattened whirlpool of hot plasma wrapped around the hole. This is the accretion disk, and it is the real source of the light we see. Imagine a ring of cars on a circular racetrack, all moving at different speeds, all bumping into each other a little. The outer cars move more slowly, the inner ones faster. Friction heats the tyres and brakes. Energy is lost from their orbits, and over time they spiral inward. Now scale that picture up until each car is a clump of gas. The racetrack is trillions of kilometres across, and the central pit is a black hole 66 billion times the mass of the Sun. The same basic principle applies. Friction and turbulence in the disk turn orbital energy into heat. The plasma in the disk around TON 618 is not gently warm. Close to the inner regions, temperatures reach millions of degrees. At those energies, atoms are stripped of their electrons, and the gas emits light across a wide range of wavelengths, from visible to ultraviolet and X-ray. Each photon is a tiny receipt from the energy budget of infalling matter, a record of gravitational potential being cashed out. Here is where the engine becomes shockingly efficient. When you look at an ordinary star like the Sun, it shines by fusing hydrogen into helium in its core. Only a small fraction of the mass involved is converted into energy. Over the lifetime of the star, the total efficiency of mass turned into light is well under 1%. In an accretion disk around a black hole, the physics is different. Matter falling deep into a gravity well can convert a far larger fraction of its mass into radiation before disappearing. Depending on the spin of the black hole and the details of the disk, efficiencies of around 10% are common, and higher values are possible. That means if you take the same amount of mass and drop it into a well-organized accretion disk, you can get 10 times or even dozens of times more energy out as light than if you burned it through nuclear fusion in stars. On a cosmic scale, that is outrageous. It turns gravity into one of the most powerful power plants in the universe. For TON 618, this power plant is being run at nearly full throttle. The disk is being fed by a constant flow of gas drawn in from its host galaxy. Some of that gas may come from the galaxy itself, stirred up by gravitational interactions and driven toward the center. Some may be funneled in by past collisions with other galaxies, events that can dump fresh fuel into the central regions and trigger violent bursts of accretion. However the fuel arrives, once it enters the sphere of influence of the black hole, the disk takes over and begins to process it. The structure of that disk is not smooth and serene, despite how beautifully it might look in artist impressions. It is a chaotic ocean of magnetic fields and turbulent eddies. Different rings of plasma try to orbit at different speeds. That difference creates shear, layers sliding past one another. Magnetic fields tie those layers together, twist, snap, and reconnect. This process drags angular momentum outward, allowing matter to drift inward. The inner regions lose energy and fall. The outer regions gain some of that angular momentum and move slightly farther out. You can think of it as a conveyor belt that transports not only mass but also motion. As matter spirals inward, each tiny step closer to the black hole costs gravitational potential energy. That energy has to go somewhere. It appears as heat, as chaotic motion of particles, and finally as radiation beaming out into space. Because the inner regions of the disk are deeper in the gravitational well, they are hotter and brighter. The disk therefore has a temperature gradient, cooler in the outer parts, blazing white-blue in the inner parts. This gradient imprints itself on the spectrum of the quasar. By studying the distribution of light across different wavelengths, astronomers can infer how hot various regions of the disk are and how that temperature changes with radius. In that sense, the light from TON 618 is a map of its own power plant. There is a limit to how hard you can run this engine before it starts to push back against itself. All that light streaming out of the disk carries momentum. When photons hit particles, they exert pressure. If the disk shines too brightly, the outward pressure of radiation can begin to counter the inward pull of gravity on the infalling gas. At some point, a balance is reached where the flow of matter and the glow of radiation settle into a kind of uneasy truce. This balance point is called the Eddington limit. For a given black hole mass, there is a characteristic maximum brightness, where gravity and radiation pressure roughly cancel. Many luminous quasars, TON 618 included, seem to operate near this limit. Running near that edge tells us something important. The black hole is being fed at a rate that keeps it bright but does not instantly choke off its own fuel supply. It is like driving a car with the accelerator pressed down just below the point where the engine overheats. You go fast, but you do not blow the system apart. While all of this is going on in the disk, the black hole itself stays utterly silent, at least in the simple picture. No light escapes from inside the horizon, yet the presence of the hole shapes everything about the way the disk behaves. The closer you get to the horizon, the faster matter must orbit in order to stay in a stable path. Inside a certain critical radius, even that is not possible, and stable circular orbits cease to exist. This radius, the innermost stable orbit, marks the inner edge of the disk. Material that crosses this inner edge plunges inward quickly, falling across the horizon in a final burst of acceleration. Most of its remaining energy goes into deepening the gravity well rather than creating more light. The glow we see comes from the region just outside that inner boundary, where the struggle between orbit and fall is most intense. Add to this the invisible choreography of magnetic fields threading through the disk and looping around the black hole, and you have the ingredients for some of the most dramatic structures in astrophysics. Under the right conditions, those fields can act like rails, channeling some of the energy and angular momentum into narrow beams that shoot out along the rotation axis of the hole. Those are the jets we will meet in detail later, but it is important to note that they are not separate from the disk, they are powered by it. So when you look at an image of a quasar in your mind, try to see past the glow. At the centre of TON 618 is a hierarchy of processes, a vast disk that converts gravitational potential into radiation, magnetic turbulence that redistributes motion and launches outflows, an inner edge where stable orbits end, a silent horizon beyond which energy disappears from the universe we can see. All of this is what lies under the light. The black hole is not a thing that sits there passively swallowing matter. It is an engine at the heart of a self-regulating system, one that can run at terrifying power levels without tearing itself apart. And because gravity is the ultimate authority in this regime, the same equations that describe a smaller black hole and disk around a stellar collapse also describe this monster, just scaled up. In TON 618, that scaling up has been pushed nearly as far as the universe seems willing to go. To understand how far the rules are stretched near the inner regions of the disk, we have to talk about where classical intuition fails, and how relativity starts to shape even the paths of light itself. Up to now, we have mostly told this story in the language of ordinary gravity. Matter orbits, friction heats it, light escapes. That picture is useful, but near a black hole like TON 618 it quietly starts to lie to you. The inner disk is not just a faster version of the outer disk. It is a place where space and time themselves begin to twist, and where the simple idea of an orbit stops behaving the way your intuition expects. In Newton's universe, if you want to orbit closer, you just go faster and hang on. Around a black hole, that rule is only partly true. As you move inward in the disk, your circular orbit must indeed be faster. The orbital period shrinks. The speeds approach a significant fraction of the speed of light, and the inner gas whips around in dizzying loops. But there is a limit. At some specific radius, a perfectly circular orbit stops being stable. A tiny nudge inward sends you into a plunge you cannot pull out of. That critical distance is called the innermost stable orbit. For a non-spinning black hole, that innermost orbit sits a few times farther out than the event horizon. For a rapidly spinning one, the story changes. If matter orbits in the same direction the hole spins, the stable orbits can exist much closer in. The disk can tuck itself deeper into the gravity well before it runs out of safe paths. If matter orbits opposite to the spin, the innermost safe orbit sits farther out. This dependence on spin is not a minor detail. It affects how hot the inner disk can get, how efficient the engine is, and how much energy per unit mass can be extracted before matter disappears across the horizon. Already you can feel relativity tightening its grip. Close to the inner edge, time itself stops behaving in the way your everyday experience has trained you to expect. A clock attached to a ring of gas in the inner disk really does tick more slowly than a clock floating far away in intergalactic space. From the point of view of that gas, everything looks normal. Processes unfold in the usual order. Orbits complete, turbulence swirls, radiation escapes. From our point of view, watching from billions of light years away, the same processes appear stretched. Signals from the deepest regions are delayed and distorted. The glow we see from the disk carries those distortions. Photons that climb out from deep in the gravity lose energy on their way up. This is gravitational redshift. Their wavelengths are stretched, so the light arrives a little redder than when it was emitted. On top of that, the gas in the disk is moving at incredible speeds. Parts of the disk are moving toward us, parts are moving away. The side hurtling in our direction has its light shifted bluer by motion. The opposite side has its light shifted redder. When you stack these effects together, the neat, narrow spectral lines that would be emitted by static, calm gas are broadened and skewed. In some active galaxies, we see ion emission lines stretched into long asymmetric shapes, with a sharp edge on one side and a long tail on the other. Those line profiles are not random scribbles, they are fingerprints of strong gravity and high-speed motion. In the case of TON 618, we do not resolve the disk directly, but we do see broad emission features and variability patterns that tell us the same basic physics is in play. Relativity also gets to work on the paths of the photons themselves. Light does not travel in straight lines through this region, in the way you might imagine straightness. The mass of the black hole curves space-time, and light follows those curves. Some photons that leave the disk headed downward can be bent back around and escape upward, giving us a view of parts of the disk that would otherwise be hidden. Others loop around the hole entirely, contributing to the strange halo-like structures we would see if we could image the region at extreme resolution. This bending is not just a curiosity. It smears out the apparent position of the emitting regions and mixes together light from different parts of the disk. It helps to shape the overall brightness pattern. When you see artistic renderings of a black hole with a glowing ring that seems to wrap above and below the dark center, that is a visualization of this effect. The top of the disk, the bottom of the disk, and the far side are all being lensed into view at once. Then there is frame dragging, a phrase that sounds like science fiction but is very real in the mathematics of general relativity. A spinning black hole does not just sit and twist by itself. Its rotation drags the very fabric of space-time around with it. Close to the hole, any object, even light, feels this twist. It is forced to swirl around in the direction of the spin. There is a region outside the horizon, called the ergosphere in the technical language, where nothing can remain at rest with respect to the distant universe. Everything is compelled to co-rotate with the hole to some extent. This dragging of space-time affects the disk and anything else wandering nearby. It can modify the paths of particles, tilt the inner disk, and help set up the conditions under which energy and angular momentum can be extracted from the rotation of the hole itself. Some of the mechanisms proposed for launching powerful jets rely on this effect. The rotation of the black hole becomes a reservoir of energy that can, in principle, be tapped. All of these relativistic effects do something subtle to our picture of TON 618. They remove the comfort of thinking in terms of simple, rigid orbits and clear, sharp boundaries. The inner disk is not just a circle of gas whirling in place. It is a region where time slows, space twists, and light paths curve in ways that defy straight-line thinking. Yet the result is not chaos without pattern. It is structured distortion. Astronomers use that structure as a tool. By measuring how quickly the brightness of a quasar changes, you can infer how large the emitting region is. If the central light output can rise and fall significantly over a period of days, the region responsible cannot be larger than the distance light can travel in those days. Combine that with the understanding of how close the inner disk can sit to the horizon, and you get constraints on the mass and spin of the black hole. The wilder the variability, the tighter the region where it must be coming from. By modelling the broadened and skewed emission lines, you can estimate how fast the gas is moving and how deep into the gravity well it sits. Different spin values lead to different predicted shapes for those lines. When you match those predictions to observations, you're effectively reading off the settings of the cosmic engine. In other words, the same physics that makes the inner region of TON 618 such a harsh, unforgiving environment also makes it the best laboratory we have for testing our understanding of gravity at its most extreme. We cannot build anything like this in a particle accelerator. We cannot recreate these conditions in a lab on Earth. We can only watch, from far away, as nature runs the experiment for us. For TON 618, the stakes are even higher. If our current theories of relativity and high-energy astrophysics can successfully describe what is happening in this monster, that is a powerful vote of confidence in those theories. If they cannot, if we find persistent mismatches between prediction and measurement, then this quasar becomes a signpost pointing toward new physics. Even now, debates continue about details of disk structure, jet launching, and the exact growth histories of such ultramassive black holes. What is not in doubt is that relativity is no longer an optional add-on in this story. It is the backbone. We have now reached a point in our journey where the gravity around TON 618 stops acting like an invisible hand and starts acting like an artist, reshaping time, space, and light into forms that are hard to imagine but very real. Yet the influence of this black hole does not stop at the edge of its disk. Its reach extends outward along narrow beams that can blaze across intergalactic space and seem to break the most famous speed limit in the universe. Those are the jets, and they are the next piece of this puzzle. So far we have stayed close to the disk, watching matter spiral inward and vanish. That is only half the story. A black hole like TON 618 does not just pull, it also throws. Some of the most dramatic things it does involve matter that does not fall in at all, but is instead hurled outward in narrow beams that can cross entire galaxies. These are the jets. Picture the accretion disk again, a colossal whirlpool of plasma spiraling around the black hole. Threaded through that disk are magnetic fields. They are not gentle field lines drawn in a textbook. They are tangled, wound up, and dragged around by the rotation of the disk and the spin of the black hole itself. Near the poles of the system, those fields can channel some of the chaos into order. They act like rails, guiding charged particles into tightly collimated beams that shoot out in opposite directions, away from the disk and away from the black hole. The particles in these beams move at speeds very close to the speed of light. They are accelerated by electric fields that arise naturally when magnetic field lines twist, reconnect, and snap. Once launched, the jets punch through the surrounding gas of the host galaxy and keep going, sometimes for hundreds of thousands or even millions of light years. In some radio galaxies, the full jet and lobe structures are larger than the visible part of the galaxy itself. For an ultramassive black hole like TON 618, the potential power in these jets is enormous. The energy source is twofold. Some comes from the gravitational energy of matter falling through the disk and being redirected into the jets. Some may come directly from the rotational energy of the black hole, tapped through the way magnetic fields interact with space-time near the horizon. In that region, frame dragging twists the magnetic field lines as if space-time itself were a spinning conductor. Under the right conditions, that twist can set up currents that extract energy from the spin and feed it into the jets. However you slice the details, the end result is astonishing. Narrow beams of plasma and electromagnetic fields, launched from a region smaller than the orbit of a planet, can carry enough energy to reshape gas clouds far beyond the galaxy that birthed them. We do not see the black hole or the jets themselves with our eyes. We see what they do to their surroundings. At radio wavelengths, the jets glow with synchrotron radiation, produced when fast-moving electrons spiral around magnetic field lines. The jets terminate in bright hotspots, where they slam into the intergalactic medium, dumping their energy into shocks that heat the gas to millions of degrees. Beyond those hotspots, the energy inflates giant lobes of radio-emitting plasma, balloon-like structures that can stretch across intergalactic space. The same electrons that shine in radio light can also scatter lower energy photons up to higher energies. When they collide with background light, they can boost it into the X-ray or even gamma-ray range. That is why some jet systems are visible all across the electromagnetic spectrum, from long wavelength radio maps to high-energy observatories that detect violent photons. In the most extreme cases, something almost mischievous happens. As material races down a jet toward us at nearly the speed of light, the timing of the photons it emits becomes strange. Light sent later from a knot in the jet can catch up with earlier light, because both the jet material and the photons are moving in nearly the same direction. On the sky, this can make features in the jet appear to move faster than light, as if nature had broken its own speed limit. In reality, nothing locally travels faster than light. It is a perspective trick, a combination of high speed and alignment that compresses time and distance in our view. Astronomers use that trick as a measuring tool. By tracking how fast these apparent motions are, and combining that with how bright and beamed the jets appear, they can infer the true speeds and angles involved. Some jets are found to be moving at more than 99% of light speed. The fact that projection effects can be so strong is itself a confirmation of just how relativistic these flows are. Now step back and look at the bigger picture again. TON 618 is not simply swallowing matter quietly. It is, or at least was in the epoch we are seeing, very likely launching outflows and jets that reach far into its environment. Those jets and winds do not politely leave the surrounding galaxy alone. When they plough into gas clouds, they can compress them and sometimes trigger star formation. More often, on large scales, they heat and disperse the gas, making it harder for that gas to cool and collapse into new stars. This is where the idea of feedback comes in. If the black hole at the centre of a galaxy grows too hungry and shines too brightly for too long, its own output begins to shut down the fuel supply. Radiation pressure from the quasar can drive broad outflows of gas from the inner regions. Jets can carve out cavities in the hot gas that surrounds galaxies and clusters, stirring and heating it. Over millions of years, these processes can reduce the amount of cold gas available to form stars. In effect, the black hole imposes a kind of self-regulation on its host galaxy. Without this regulation, our theoretical models of galaxy formation run into trouble. Simulations that include only gravity and simple gas cooling tend to produce galaxies that are too massive and too full of stars compared to what we see in the real universe. Add in the energetic feedback of active galactic nuclei powered by black holes and their jets, and the match improves. Suddenly, there is a way to keep galaxies from overgrowing, to stop them from turning all their gas into stars at once. For an ultramassive black hole like the one in TON 618, the scale of that influence is staggering. The jets and radiation do not just brush the nearby clouds. They can affect the entire galaxy, and even the thin intergalactic gas beyond. They can seed surrounding space with magnetic fields and high-energy particles. They can leave behind ghostly radio lobes that persist long after the central engine has quieted down. So when we say TON 618 sits at the centre of a galaxy, that phrase is almost misleading. It suggests a small object tucked away in the middle, a passive point around which everything else merely orbits. The truth is closer to the opposite. The black hole is an active participant in shaping the fate of its host. It is a furnace whose exhaust flows out in beams that stitch the galaxy into the larger cosmic web. We will eventually come back to what this means for the growth limits of such monsters. For now, the important thing is to see TON 618 not just as a sink, but as a source of energy, of radiation, of jets that seem to outrun light, of feedback that can quench or trigger the birth of stars. Having seen how its influence extends far beyond the event horizon, the natural question is how we can weigh something like this at all. We are still very far away. All we have are photons, flickers, and spectra. Next, we will turn to the detective work that lets us measure an invisible giant across 10 billion light-years. At some point in this story, a healthy doubt kicks in. You hear numbers like 66 billion suns and a radius that could gulp down our entire solar system, and a small voice in the back of your mind says, "Really? How can we possibly claim such specific figures about something we cannot see, in a galaxy we cannot resolve, at a distance of 10 billion light-years? That voice is not a problem. It is exactly the voice astronomers listen to every day. So let us slow down and trace the chain of evidence together. On our own doorstep, near the centre of the Milky Way, we can weigh a black hole the simple way. We watch stars orbiting an invisible mass. We measure how fast they move and how close they get. The faster a star circles at a given distance, the more mass must be pulling on it. This is basic gravity. You can do the same trick with planets around a star, moons around a planet, or gas clouds around a galaxy. Motion under gravity is a scale that weighs whatever is at the centre. For distant quasars, we cannot see individual stars whipping around the black hole. They are far too small on the sky, but we can see something else that moves under gravity. We can see clouds of gas. Surrounding the accretion disk in an active galaxy is a region of fast-moving gas that glows in specific colours of light. Astronomers call this the broad line region. It earns that name because the spectral lines it produces are not narrow spikes but smeared out bands. That smearing happens because the gas is racing around the black hole at thousands of kilometers per second. Gas moving toward us shifts its light a little bluer. Gas moving away shifts it redder. Mix together light from all those directions and you get a broadened feature. The width of those lines is a direct clue to the speeds involved. Think of a crowd of cars on a circular racetrack. If they all drive slowly, the noise they make has a gentle spread of pitches. If they scream around at high speed, the range of pitches becomes much wider because the Doppler effect is stronger. The same is true for light. The broader the emission line, the faster the gas is moving. Speed alone is not enough to weigh the central mass. You also need distance. A small mass can hold on to fast-moving gas if the gas is very close. A larger mass can hold on to the same speeds at much greater distances. What astronomers need is the size of the broad line region. That is where one of the cleverest tricks in modern astronomy comes in. Quasars flicker. The light from the accretion disk does not stay perfectly steady. It brightens and dims over days, weeks and months as clumps of gas fall inward and local instabilities flare and then calm down. When the central disk brightens, it sends extra light outward in all directions. Some of that light eventually hits the surrounding gas clouds in the broad line region. When those clouds are lit up more strongly, they respond by glowing more strongly in their own emission lines. To an observer far away, that response looks like an echo. First, you see the central continuum light from the disk rise. Then, after a delay, you see the strength of the broad emission lines increase. The delay is set by the light travel time between the disk and the gas clouds. If the broad line region is fairly close in, the delay is short. If it is farther out, the delay is longer. Measure that lag carefully by monitoring the quasar over time, and you have a direct estimate of the size of the region. This method is called reverberation mapping, and it turns time into a ruler. Once you know the characteristic speed of the gas from the line width, and the characteristic radius of its orbit from the time delay, gravity does the rest. A heavier central mass requires faster motion to keep the gas bound at that radius. Combine the numbers, and you can solve for the mass of the black hole that must be lurking in the middle. The details involve the virial theorem, a relationship between kinetic and potential energy in bound systems, but the core idea is simple. Fast plus far means heavy. Astronomers have applied reverberation mapping to many closer active galaxies and quasars, where long campaigns of monitoring are possible. These measurements build up a library that links three things: the luminosity of the quasar, the size of the broadline region, and the typical speeds of the gas. Patterns emerge. Bright quasars tend to have larger broadline regions. The relationship between luminosity and region size becomes tight enough that it can be used on its own. This is where TON 618 comes in. At its enormous distance, we do not have the luxury of detailed reverberation campaigns that track its every flicker. The timescales are long, and the object is faint compared to nearby targets. Instead, astronomers use the calibrations built from closer quasars. From the overall luminosity of TON 618, they infer the likely size of its broadline region. From the width of its broad emission lines, they infer the gas speeds. Put those together, and the same gravity-based argument gives a mass in the tens of billions of suns. You might worry that this sounds dangerously indirect. It is. There are uncertainties at every step. The thickness and shape of the broadline region, the exact geometry of the gas clouds, the angle at which we are viewing the disk and region, all of these can tweak the result. Individual mass estimates can easily be off by factors of a few, yet even with generous error bars you do not get a modest black hole. You still land in a range where the mass is truly extreme, and crucially, there is more than one way to cross-check. Another line of reasoning starts from the brightness of the quasar and the concept we met earlier, the Eddington limit. For a given black hole mass, there is a maximum steady luminosity at which the outward push of radiation on infalling gas roughly balances the inward pull of gravity. Many luminous quasars seem to operate near this limit. If you measure how bright TON 618 is and assume it is shining at some fraction of its Eddington power, you can invert the logic. The brightness implies a minimum mass needed to keep the engine from blowing itself apart. That calculation again lands in the realm of tens of billions of solar masses. You can also look at the bigger pattern across many galaxies. In nearby universes, where we can measure both the mass of central black holes and the properties of their host galaxies, a tight relationship appears. More massive black holes tend to live in galaxies whose central regions have stars moving with larger random speeds. This link between black hole mass and the velocity spread of stars in the bulge suggests that galaxies and their central black holes grow together. Extrapolate that relationship upward, and a 60 billion solar mass black hole would be expected to sit in a truly gigantic galaxy. We cannot yet see the host of TON 618 in fine detail, but what we can detect is consistent with a massive environment. Nothing about the surrounding light argues for a tiny ordinary system somehow hiding an absurdly outsized black hole. The picture that emerges is of a giant living where giants live, so the case does not rest on a single measurement or a single model. It rests on a network of clues, broadline widths that are too large to be explained by anything but a deep gravity well, a luminosity that demands a huge mass if the system is not to blow itself apart, scaling relations from galaxies where both black hole and stars can be weighed directly, libraries of reverberation mapped quasars that tell us how large a bright broad line region should be. Together, these strands of evidence braid into one conclusion. TON 618 is an ultramassive black hole in the regime of tens of billions of suns. Could the exact number change as our methods improve? Absolutely. Future observations might nudge the estimate up or down, they might reveal structure in the host galaxy that refines the story. But what will not change is the headline. This is a monster. No reasonable tweak to the inputs turns TON 618 into a modest object. In a way, this is where you stop being a passive viewer and become part of the investigation. You now know the key ideas astronomers use to weigh the invisible: speed, size, light, and time. You could pick up the spectrum of a quasar yourself and read it not as a pretty graph, but as a set of arguments. You could follow the chain from flicker to echo to radius to mass. We have answered how we can claim such a ridiculous weight for an object we will never visit. Now the next natural question is how we know where and when in the universe that object truly is. Because in astronomy, distance and time are two sides of the same problem. That is where redshift, expansion, and the strange idea of looking back in time through a telescope enter the story. By now we keep throwing around a phrase that sounds simple and is anything but. TON 618 is about 10 billion light-years away. It sounds like we're reading off a label on a map. Pushpin here, distance written next to it. The reality is more tangled. In an expanding universe, distance and time share a passport. To say how far away a thing is, you have to say when you're talking about. The main clue baked into the light from TON 618 is something called redshift. Every atom has its own set of favourite colours, specific shades of light it absorbs or emits when its electrons jump between energy levels. In a laboratory on Earth, those shades appear at very precise wavelengths, and we can measure them. When we look at starlight or galaxy light, we see the same patterns written into the spectrum: hydrogen, helium, oxygen, iron. Each leaves a recognisable fingerprint. Now imagine taking that fingerprint and stretching it. In the spectrum of a distant quasar, almost every line appears shifted toward the red end of the scale. The pattern is the same, but all the features have slid to longer wavelengths. The amount of shift tells us how much the universe has expanded during the time the light has been travelling. Light left the quasar with one set of colours, then spent billions of years crossing space that was growing under its feet, so to speak. By the time it arrives, every wave has been stretched. We call the amount of that stretch the redshift. You can think of it as a kind of cosmic mileage reading. The higher the redshift, the longer the journey, and the younger the universe was when the light began its trip. For TON 618, the redshift is high enough that we know we are looking deep into the past, to a time when the universe was less than half its current age. This is not just a neat trick with colours, it is tied to the motion of galaxies on the larger scales. In the early 20th century, astronomers noticed that light from most galaxies is redshifted in a way that increases with distance. The farther away a galaxy is, the faster it appears to be receding from us. This is not because we sit at a special centre and everything is running away from us. It is because space itself is expanding, carrying galaxies along like raisins embedded in rising dough. Measure the relationship between distance and apparent recession speed carefully, and you get the expansion rate of the universe. At modest distances, this is called the Hubble law, though at the scales of TON 618 the situation is more complicated. The expansion rate itself has changed over cosmic time, slowed by gravity, then later sped up by dark energy. But the core idea remains. The universe has a history of expansion, and redshift is a record of that history imprinted on every ancient photon. To use redshift as a distance tool, you first have to calibrate it. That is where the cosmic distance ladder comes in. Near Earth, within a few thousand light years, we can measure distances directly using parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars. The size of that tiny wobble tells us how far away the star is. It is like holding up a finger and closing one eye, then the other, and using how much your finger seems to jump to guess how close it is. Farther out, parallax becomes too small to measure easily, so we need a new rung on the ladder. Certain stars, such as Cepheid variables, pulse in brightness in a regular way. Their true power is linked to the period of their pulsations. By measuring how fast they blink and how bright they appear, we can infer their distance. These stars serve as standard candles, objects with known luminosity that can be used to mark distances across nearby galaxies. Beyond that, we use even more powerful standard candles. Some types of exploding stars, called Type 1 supernova, have relatively uniform peak brightness. When we catch one in a distant galaxy, we can again use its apparent brightness as a distance marker. Combine those measurements with redshift, and you can see how the expansion of the universe has changed over time. Step by step, rung by rung, this ladder extends from stars in our neighbourhood to galaxies billions of light years away. Each method overlaps with the next, allowing cross-checks. If one rung were badly wrong, the mismatch with neighbouring rungs would be obvious. By the time we reach the realm of very distant quasars, we are no longer measuring their distances with parallax or even directly with standard candles. Instead, we rely on the calibrated relationship between redshift and distance in the context of a cosmological model that has been tested against many kinds of data. The light from the cosmic microwave background, the distribution of galaxies on large scales, the brightness of distant explosions, all of these feed into a coherent picture of how the universe has expanded. Within that picture, A given redshift corresponds to a specific look-back time and to several ways of defining distance. There is the distance the light has actually travelled. There is the distance between us and the object right now if you could freeze cosmic expansion this instant and lay down a ruler. There is the distance at the time the light was emitted. For a quasar like TON 618, those numbers can differ by billions of light years. So when we casually say 10 billion light years away, we are compressing a lot of nuance into a single phrase. What we really mean is something like this. The light has been travelling for on the order of 10 billion years of cosmic time. The universe was significantly younger and denser when that light left the quasar, and today, if you could somehow draw a straight line through the expanding fabric of space between us and where TON 618 once was, the length of that line would be even greater than the light travel distance. This is what turns powerful telescopes into time machines. When you point a radio dish or an optical mirror at a distant quasar, you are not seeing it as it is now. You're seeing it as it was when the universe was young and quasars were more common. You are looking into an earlier chapter of cosmic history, one in which galaxies were still rapidly assembling and black holes were growing at furious rates. That is not just poetic language. It has practical consequences. If we observe a lot of quasars at different redshifts, we can see how their population changes over time. At some epochs, quasars are abundant and luminous. At later times, they become rarer and dimmer. By the present day, most massive black holes are quiet, either because they have run out of fuel or because their host galaxies have settled into more quiescent states. TON 618 lives near the peak era of quasar activity. That makes it a key witness to the phase of the universe when central black holes and galaxies were rapidly co-evolving. The redshift also tells us something about the cosmic environment in which this monster grew. At high redshift, the average density of matter in the universe was much higher than it is now. Gas clouds were more tightly packed. Collisions between galaxies were more frequent. Streams of cold gas could flow into forming galaxies along the filaments of the cosmic web, providing fresh fuel. Under those conditions, a black hole with a good starting mass and a favourable feeding history had more opportunity to grow quickly. Yet even in that rich environment, pushing a black hole up to tens of billions of solar masses by the time we see it remains a challenge for our models. That is one reason TON 618 matters so much. It is not just far and bright, it is awkward. It sits at a combination of mass and age that tests our assumptions about how early the seeds formed and how efficiently they accreted. So the next time you hear an astronomer say this object is at redshift 2 or 3, or this galaxy is 10 billion light years away, you can translate the phrase into its deeper meaning. They are saying here is a fossil of a younger universe. Here is a scene from a much earlier page of the story, delivered to us on a beam of light that has been stretched and delayed by the very expansion we're trying to understand. For TON 618, that story includes not only its current monstrous size, but also the conditions that allowed such a monster to exist so early. To grasp those conditions, we have to zoom out yet again, this time not in space, but in time, and watch how the young universe built the scaffolding on which galaxies and black holes like this could form. That takes us all the way back to the first structures, the first stars, and the cosmic building program that set the stage for everything that followed. By the time the light of TON 618 reaches us, the universe has already done most of the hard work. Galaxies exist. Massive black holes sit in their centres. The cosmic web is in place. To understand how a monster like this could appear so early, we have to rewind far beyond its own birth, back to a time when there were no stars, no galaxies, and certainly no quasars, only a hot, expanding fog with tiny imperfections. Right after the Big Bang, the universe was almost perfectly smooth. Everywhere you looked, the density was nearly the same, with only minuscule variations. Those variations are frozen into the cosmic microwave background, that faint glow of leftover radiation that now fills all of space. In that glow, we see slightly warmer and cooler patches. Those patches mark places where the density was slightly higher or lower than average. Those tiny differences did not stay tiny. Gravity is greedy. Regions that start just a little denser pull more matter toward themselves. That extra matter makes them denser still, which pulls in even more. Over millions of years, those small ripples in density grow into real structures. But gravity does not act only on the matter you can see. It also works on dark matter, the invisible component that outweighs ordinary atoms by a large factor. Dark matter does not feel light, but it does feel gravity. As the universe expands and cools, dark matter begins to clump into halos, invisible cocoons of mass scattered throughout space. Ordinary gas falls into these halos, pulled in by their gravity like mist gathering in valleys. The halos grow by merging with one another and by accreting more matter from their surroundings. Over time, they trace out the same filamentary pattern we now call the cosmic web. Inside the deepest parts of those halos, where gas piles up and cools, the first stars are born. These first-generation stars were very different from the familiar stars in our present sky. They formed from pristine hydrogen and helium, with almost no heavier elements. Without those heavier atoms to help the gas cool and fragment, the first stars tended to be much more massive. Many times the mass of the Sun, sometimes hundreds of times. They burned hot and fast, living only a few million years before dying in spectacular explosions. Those explosions blew the first heavier elements back into space: carbon, oxygen, silicon, iron. In doing so, they changed the rules for all future generations of stars. Now, gas clouds could cool more efficiently, break into smaller pieces, and form a wider range of stellar masses. At the same time, some of the most massive first-generation stars may have collapsed almost entirely into black holes, leaving behind relatively heavy seeds embedded in their dark matter halos. While this was happening at small scales, the large-scale universe kept evolving. Halos merged with halos. Where two halos of similar size collided, their gas could be shocked, compressed, and cooled again, forming new waves of stars. Many of the galaxies we see today are the product of long chains of such mergers, stitched together over billions of years. In the early universe, around the time TON 618 lived, this process was happening at a frantic pace. Galaxies were smaller on average, but interactions between them were more common. The cosmic web was busy. Gas did not only arrive in sudden collisions. Simulations suggest that in the early universe, thin streams of cold gas could flow along filaments directly into the centers of forming galaxies. These cold flows acted like cosmic rivers, delivering fresh fuel straight to the regions where stars and black holes could grow. In that era, galaxies were less settled and more clumpy, with giant star-forming regions and turbulent disks. This combination of ingredients created a remarkably fertile environment for black hole growth. Start with a seed black hole, either from the collapse of a massive star or from an even more dramatic event. Place it in a region where gas is abundant, where mergers are frequent, and where cold flows can keep delivering fresh fuel. Each time the host galaxy collides or interacts with another, gas can be funneled toward the center by tidal forces, feeding the black hole. Each burst of accretion can light up the nucleus as an active galactic core, a smaller cousin of the bright quasars we see at higher powers. There is another possibility that may have played a role in creating the earliest massive seeds. Under the right conditions, a large cloud of gas in a dark matter halo might avoid fragmenting into many stars and instead collapse more directly into a single huge object. If that object becomes unstable and collapses further, it can produce a black hole with a mass far larger than any single ordinary star. These direct collapse black holes would start the race already several steps ahead, with masses of hundreds of thousands of suns or more. Whichever path nature prefers, the key point is that the early universe did not wait quietly for a long time before building large structures. It started right away. Within a few 100 million years, there were already galaxies with active star formation. Within the first billion years, there were quasars whose black holes weighed hundreds of millions of solar masses. TON 618 pushes that trend to the edge, sitting in a mass range that challenges even generous growth histories. Think about the timeline from another angle. At the redshift where we observe TON 618, the universe is maybe a few billion years old. A black hole that already weighs tens of billions of suns at that moment must have grown at an almost relentless pace. Either it started as a very heavy seed and accreted steadily near its maximum sustainable rate, or it experienced periods of wild, super-efficient feeding that our standard pictures struggle to capture. In either case, the growth story is tied directly to the environment. No amount of hunger helps if there is no gas. This is why the scaffolding built by the early universe matters so much. Without dark matter halos to gather gas, there would be no gravitational wells to host galaxies. Without the first stars to enrich the gas, later cooling and star formation would look different. Without frequent mergers and cold flows, central regions would not be fed often enough to sustain long-lived quasar phases, By the time TON 618 lights up as the blazing quasar we see, it sits at the intersection of all these processes. It lives where several filaments of the cosmic web likely converge. It inhabits an overdense region that collapsed early and hard. It draws on gas that has been processed by multiple generations of stars and stirred by multiple collisions. Its host halo is not a modest structure. It is one of the richest cradles the young universe can offer. From our vantage point in a calmer later epoch, this can be easy to forget. The night sky looks serene. Galaxies drift slowly. Space seems mostly empty and quiet. But when you look back to the time of TON 618, you are seeing the aftermath of a frenzied construction boom. The cosmic web was still tightening. The average density was higher. Gravity was still rearranging matter on every scale it could reach. TON 618 is not an isolated freak event dropped into that story from nowhere. It is an extreme product of that environment, a demonstration of what is possible when you give gravity time, dark matter to sculpt the stage, gas to pour in, and a seed black hole in the right place. The puzzle, and the opportunity, is that even in such a generous setting, building something this big, this fast, is not trivial. To test our ideas about how that could happen, we now have to zoom in on the growth process itself. How do you take a seed black hole and feed it in a universe that is itself changing around it? And what limits, if any, does nature impose on that growth? That is the question at the heart of the next part of our journey. We have the stage, the fuel, and the monster. Now comes the uncomfortable math. At the redshift where we see TON 618, the universe is only a few billion years old. Yet the black hole already weighs tens of billions of suns. That is not a gentle stroll through cosmic time. That is a sprint. The question is how you get from a tiny seed to this scale without breaking the rules of physics on the way. Every growth story starts with a seed. One possibility is a black hole left behind when a very massive first-generation star dies. These seeds might weigh tens of suns, maybe a few hundred at most. They form early, but they are small. Another option is more dramatic. Under special conditions, a whole cloud of gas in a young galaxy might collapse almost directly into a black hole without fragmenting into many stars first. That kind of direct collapse could create a seed with a mass of hundreds of thousands or even a million suns right from the start. You can also imagine runaway collisions in the dense core of a young star cluster, where big stars keep merging into a single giant that then collapses. Or even more exotic ideas like primordial black holes formed in the earliest instance of the universe. The details differ, but the lesson is simple. The heavier the seed, the less work the universe has to do later. Once a seed exists, it has two main ways to grow. It can merge with other black holes, and it can eat. Mergers happen when galaxies collide and their central black holes sink toward each other and eventually coalesce. Each merger adds the masses together, minus a little loss to gravitational waves. Over many mergers, you can build something larger. But mergers alone are not fast enough to reach tens of billions of suns by the time of TON 618. They help. They are not the whole story. The real engine is accretion, the process we have already seen in action in the accretion disk. Gas falls in, heats up, and radiates. The catch is that when you radiate energy, you also push back on the very gas you are trying to swallow. Bright light exerts pressure. Above a certain point, the outward shove of radiation on the infalling gas can balance the inward pull of gravity. That balance point is the Eddington limit. For a given black hole mass, there is a characteristic maximum steady luminosity, where inflow and outflow reach a kind of uneasy truce. At roughly this limit, something elegant happens. The rate at which the black hole can gain mass becomes tied to its own mass. A more massive hole can shine more brightly without blowing its fuel away, and so can accrete more quickly in absolute terms. The result is exponential growth. The mass can double over a fixed characteristic time, often called a salpeter time in the technical literature, which is on the order of tens of millions of years for typical assumptions about how efficiently mass is turned into light. Run that doubling game in your head. Start with a seed of 100 solar masses. Double it every 50 million years or so. After 10 doublings, you're at about 100,000 solar masses. After 20 doublings, you're near 100 million. After 25 doublings, you're in the billions. That sounds promising until you remember the clock. To get 20 or more doublings at a steady pace, you need accretion close to the Eddington rate, for on the order of a billion years or more, with almost no long breaks. The universe can do steady, but can it do that steady? Real galaxies are messy. gas supply is episodic. Feedback from the growing black hole can blow away or heat the very gas it needs to keep eating. Mergers may deliver fresh fuel, but also stir and heat it. Observations of quasar populations suggest that individual bright phases might last tens of millions of years at a time, then fade. Stitch enough of those episodes together and you can still reach huge masses, but the duty cycle becomes important. How often is the black hole near its maximum feeding rate versus starving? Now add in the fact that TON 618 does not just weigh a billion suns, it weighs tens of billions. That pushes any simple Eddington growth story to its limits. If you start from a small stellar remnant, you need a long run of near-perfect conditions. If you start from a heavier direct collapse seed of, say, 100,000 or 1,000,000 solar masses, the math is kinder but still strict. You have to use a big fraction of the available cosmic time at high accretion rates, and you have to live in a very rich patch of the universe. This is where super Eddington accretion enters the picture. The classical Eddington limit assumes a simple spherical flow of gas and a specific way in which light interacts with the material. In practice, accretion disks can be thick and clumpy. Radiation can escape more easily in some directions than others. If most of the light leaks out along the poles, the gas in the plane of the disk may feel a weaker push. In such geometries, it may be possible for matter to fall in faster than the naive Eddington argument would allow, at least for certain periods. Simulations show that in very gas-rich environments, with chaotic inflows and thick disks, black holes can experience bursts of accretion that effectively outrun the simple limit for a while. They glow brightly, but a lot of the energy escapes without completely blowing out the fuel. If TON 618 had multiple episodes like that early on, it could have grown faster than a smooth, steady model would predict. Mergers also stack the deck. Each time two galaxies of similar size collide, their central black holes may eventually merge. When that happens, their masses simply add, aside from a portion radiated away in gravitational waves. A black hole that has already grown to 1 billion solar masses can jump to 2 billion in a single event if it meets an equal partner. Multiply that over several major mergers, and you can climb the ladder more quickly than accretion alone would allow. But mergers bring their own complications. The merged hole can be kicked by the asymmetric emission of gravitational waves. In extreme cases, these kicks might even eject a black hole from the center of its galaxy, cutting it off from fuel. The spins of the merging holes affect the outcome. Their spins also affect how efficiently accretion converts mass into light. A rapidly spinning black hole radiates more energy per unit mass accreted. That makes it harder to grow in mass because more of the infalling material is turned into light instead of staying in the hole. This creates a subtle tension in the story of TON 618. On the one hand, its quasar phase and any powerful jets it may have had suggest a rapidly spinning black hole, since high spin tends to make disks more efficient and jets more powerful. On the other hand, high radiative efficiency means that for the same amount of gas you gain less mass. Growing to tens of billions of suns quickly becomes harder. One way out is to imagine a growth history where the black hole spends its early life accreting in a way that does not spin it up too much, perhaps through many randomly oriented episodes that cancel out each other's spin effects, and only later settles into a coherent high-spin, high-efficiency state. Another way out is to admit that we may not yet have the full picture. Our models of gas flows in the early universe are still improving. New simulations that include more detailed physics of radiation, magnetic fields, and turbulence sometimes find surprising pathways for rapid growth that were not obvious in earlier, simpler calculations. Observations of other very massive black holes at high redshift keep adding pressure. TON 618 is part of a growing pattern. It is one of the most extreme, but it is not alone. What is clear is that the growth of such an ultramassive black hole is not a quiet background process. It is a major event in the life of its host galaxy and its surrounding environment. Each burst of accretion pumps energy into the galaxy. Each merger rearranges stars and gas. The black hole and the galaxy do not grow independently. They co-evolve, influencing each other in feedback loops that are still being mapped out. In that sense, TON 618 is not just a question about one object. It is a question about limits. How big can a black hole get before the universe itself pushes back? How much can you feed one before its own radiation and jets clear out the pantry? How does spin change the game? These are the questions that lead directly into the idea of self-regulation and upper bounds, and into the puzzle of whether TON 618 is rare simply because the right conditions are rare, or because it is brushing up against a hard ceiling written into the laws of physics. To tackle that, we need to look at the feedback between black hole and galaxy, and at the theoretical arguments that suggest there may be a maximum mass beyond which black holes simply cannot grow. There is a point in this story where you have to stop asking how big TON 618 is, and start asking how big anything is allowed to be. Gravity loves to grow structures, but it does not get to play alone. Every time a black hole feeds, it talks back to its surroundings through light, winds, and jets. The more massive and active it becomes, the louder that conversation gets. The question is whether that feedback eventually turns into a hard ceiling that stops growth, or only into a soft nudge that makes monsters like TON 618 rare but possible. We have already seen the basic idea. As gas falls into the accretion disk, it heats up and shines. That light pushes on nearby matter. At low brightness, gravity wins, gas keeps falling, and the black hole grows. Near the Eddington limit, radiation pressure starts to fight back. Gas is driven into outflows, blown away from the centre instead of sinking in. On even larger scales, the combined energy of light, winds, and jets heats and stirs the gas filling the host galaxy and its halo. Picture a galaxy trying to cool its gas so that it can form more stars and also feed its central black hole. Now picture a quasar in the middle turning on like a blowtorch. Intense radiation can strip electrons from atoms, heating the gas and making it harder to cool. Wide-angle winds from the inner regions can slam into the interstellar medium and sweep it out of the central zones. Jets can pierce through the halo and dump energy into giant bubbles, keeping the surrounding gas hot and buoyant. All of these processes make it harder for cold, dense gas to reach the centre. This is feedback in action, and it appears to be essential for understanding real galaxies. When astronomers run large computer simulations that include only gravity and simple cooling, galaxies tend to grow too massive and form too many stars compared to what we observe. Add in strong feedback from supernovae and from active black holes at the centres, and the simulated galaxies become more realistic. Star formation slows in massive systems. Gas reservoirs are depleted or kept warm. The central black hole and the stellar bulge settle into the kind of tight mass relationship we see in the local universe. From this point of view, TON 618 does not simply sit in its host galaxy like an overfed guest. It is a building inspector with a flamethrower. Each time it shines as a quasar, it threatens to shut down its own supply lines. If it grows too fast, its output can sweep away the very gas that would let it grow further. That is why some theorists speak of an upper mass scale where self-regulation becomes nearly impossible to beat. Above a certain size, any additional growth triggers feedback strong enough to starve the black hole. There are more direct physical arguments as well. In the inner parts of a galaxy, gas settles into a disk influenced not only by the black hole, but also by the gravity of the stars and dark matter. If the black hole becomes too massive compared to the surrounding potential, the disk structure can change. In some models, beyond a certain mass, the gas can no longer form a stable, thin accretion disk on large enough scales. Instead, it becomes thick, clumpy, and inefficient at delivering material inward. The feeding pipeline chokes, not because the universe has run out of gas, but because the engine cannot accept it in an orderly way. When researchers take these ideas and push them through equations and simulations, they tend to find a rough upper limit in the neighbourhood of 100 to a few hundred billion solar masses for central black holes. Above that, feedback and disk instabilities make sustained growth extremely difficult. TON 618, sitting in the tens of billions range, lurks uncomfortably close to that territory. It is not at the absolute edge, but it is not safely below it either. It is near the warning label, yet mass is only half of the specification sheet. The other half is spin. If mass tells you how heavy the black hole is, spin tells you how fast it is rotating. Spin changes everything. A rapidly spinning black hole drags space-time more strongly, pulls the innermost stable orbit closer in, and allows accreting matter to fall deeper into the gravity well before crossing the horizon. That deeper fall means more gravitational energy can be converted into light. So for the same amount of mass, a high spin hole can shine more brightly. In other words, high spin makes the engine more efficient. At first glance, this sounds like a gift. A more efficient engine for a quasar as bright as TON 618 fits the picture of an extreme object. But remember the growth story. If each kilogram of mass that falls in produces more light, then for a given observed luminosity, the black hole must actually swallow less mass per unit time. High efficiency means slower mass gain. That deepens the tension we met before. To reach tens of billions of suns quickly, you want the engine to be inefficient so that most of the infalling matter ends up in the hole rather than in the glow. Spin also affects jets. Many models for powerful relativistic jets rely on the idea that magnetic fields anchored in the accretion disk and threading the horizon can tap into the rotational energy of the black hole. The faster it spins, the more energy is available to be channeled into jets that burst out along the poles. Observationally, some of the brightest jet sources in the universe do seem to require high spin to explain their power. If TON 618 ever launched enormous jets, that would be one more hint that its spin is not small. So the universe gives us this awkward trade. To explain luminous, jet-producing quasars, we are pushed toward high spin. To explain rapid mass growth to ultramassive scales, we would prefer low spin and lower efficiency. The way out is to realize that spin is not fixed at birth. It is a history. If a black hole grows mostly by steadily swallowing gas that always comes in with the same overall direction of rotation, each bit of accreted matter adds not only mass but also angular momentum. Over time, this spins the hole up toward a maximal state. In this picture, a black hole that lives in a disk galaxy with a long-lived ordered inflow can easily become a fast spinner. On the other hand, if growth happens through many short, randomly oriented accretion episodes, or through frequent mergers with other black holes whose spins point in different directions, the overall spin can be kept more modest. Contributions cancel rather than align. Which history belongs to TON 618? That is exactly the problem. Mass leaves fingerprints in many places. Spin does not advertise itself as clearly. We can infer spin indirectly by modelling the innermost regions of accretion disks in X-ray light, by looking at how close the disk seems to come to the horizon, or by studying the shape of certain broadened emission lines. For nearby active galaxies and stellar mass black holes, such measurements suggest a range of spins, some low, some extremely high. For distant quasars like TON 618, the game is much harder. The data are fainter and less detailed. The signatures are blurred by distance and complexity. This uncertainty is not just a technical nuisance, it is central to the story. If TON 618 turns out to host a rapidly spinning black hole, then our models of its growth must explain how it climbed to its huge mass without being slowed too much by high-efficiency accretion. If instead it hides a more modest spin, we must explain how it powered a quasar phase of such intensity and perhaps powerful jets without drawing heavily from rotational energy. Either way, the answers feed back into the question of limits. In the end, the idea of an absolute maximum mass for black holes might be less like a brick wall and more like a steep cliff. As you climb higher in mass, growth becomes more difficult. Feedback grows stronger. Spin effects matter more. The pool of galaxies with enough fuel shrinks. Somewhere up that cliff, the universe stops making heavier black holes simply because the path becomes too narrow and demanding. TON 618 looks very much like a climber near that cliff face. Big enough to scare our theories, but not yet so big that we throw them out. Just big enough to force us to check every assumption about feedback, fueling, and spin. We have now pushed our understanding to the outer description of this monster. Its mass, its light, its influence, its possible limits. To go any further, we have to do something stranger. We have to stop standing outside the horizon and start imagining what it would be like to fall in. That means returning to the event horizon itself and looking more closely at what that boundary really is. We have spent a lot of time circling TON 618 from the outside. We have watched its disk blaze, its jets carve through space, its gravity twist light and time. In your mind, the black hole itself may still feel like a kind of cosmic trapdoor, a sharp edge in space where things simply vanish. It is an easy picture to fall into because our instincts like walls and edges and surfaces you can point at. But the event horizon is stranger than that, and more subtle. To understand what really happens when you cross it, we have to stop thinking like engineers and start thinking like space-time. The event horizon is not a solid shell. There is no crust, no membrane that smashes into you. It is a boundary in geometry, the dividing line between places where it is still possible in principle to escape to the wider universe and places where it is not. Outside the horizon of TON 618, there are paths through space-time that a beam of light can take and still eventually wander off into intergalactic space. Inside, those paths simply do not exist. Every future route is bent inward. Here is one way to picture it. At every point in space-time you can imagine a little cone that shows all the possible directions a flash of light could travel, and inside that cone all the slower paths that matter, like you and me, could follow. Far from any mass, those cones stand straight up in time. You can move in any space direction as long as you move steadily forward in time. As you approach a massive object, the cones begin to tip toward it. At the event horizon, they tip so far that every possible future path, even for light, points toward the center. From far away, this tipping shows up as a strange slowdown. If you watch an object fall toward a black hole from a safe distance, you never quite see it cross the horizon. Its clock appears to tick more and more slowly. Its signals arrive more and more redshifted and delayed. It seems to hover just above the boundary, fading and reddening, never quite gone. This is not because the object is actually frozen in place. It is because the light it sends you has to climb out of a deeper and deeper gravitational well, losing energy and taking longer to arrive. From the point of view of the falling object, the story is very different. There is no drama at the horizon itself, no sudden feeling of impact, no change in local physics. Your own clock ticks normally, your heartbeat does not stutter. You drift through a region of space that looks, for a moment, almost ordinary. The only giveaway, if you have instruments sensitive enough, is that more and more of the universe behind you appears compressed and blue-shifted, and more of the universe ahead is cut off. But there is no visible sign marking the boundary you have just crossed. This is one of the cruelest tricks of black hole physics. The place where escape becomes impossible does not announce itself with fireworks. The universe does not raise a fence. It quietly changes the structure of future time. Once you're inside the horizon, the direction that used to mean inward toward the center is no longer a direction you can choose to go or not go. It has become as inevitable as tomorrow. Moving forward in time and moving toward the singularity are now the same thing. According to general relativity, the singularity of a black hole is not a location in space in the usual sense. It is a moment in your future, a place where the curvature of space-time becomes so extreme that the theory itself predicts its own breakdown. Outside the horizon, your world line, the path you trace through space-time, can wander across the cosmos and never encounter that moment. Inside, every future-directed world line ends there. You can change how you fall. You cannot change the fact that you fall. For TON 618, the scale of this geometry has a surprising consequence. The strength of tidal forces at the horizon decreases as black hole mass increases. Put simply, the larger the hole, the gentler the stretching and squeezing at the boundary itself. A stellar mass black hole can tear you apart even before you reach the horizon. An ultramassive black hole like TON 618 can have a horizon where the difference in gravity between your head and your feet is small enough that you could, in principle, survive the crossing in one piece. That does not mean the journey is safe. It means the worst of it comes later. You could imagine, in thought, drifting in a sturdy ship through the accretion disk environment, somehow avoiding the jets and the radiation, and then gliding down toward the black sphere defined by the horizon. Instruments on board would notice the outside universe doing strange things. Signals from distant galaxies would arrive more and more redshifted. Messages you sent outward would take longer and longer to escape. But as you crossed the horizon itself, nothing dramatic would happen locally. No flash, no crunch, no wall. Outside observers, if any survived and were watching, would disagree about when you vanished. To them, your image would dim and smear and creep ever closer to the horizon, approaching it but never quite disappearing. In their coordinates, you would take an infinite time to reach the boundary. In your coordinates, measured by your own clock, the crossing would take a finite time. This is not a paradox. It is a reminder that time is not absolute. Different observers slice space-time into moments in different ways. Once you have crossed, the roles of space and time inside the horizon become tangled. The coordinate that used to measure your distance from the center becomes more like a time coordinate. You cannot keep that coordinate constant any more than you can stop tomorrow from arriving. You can still move around a little in the angular directions, circling as you fall, but all of those motions are now riding on top of an inexorable slide inward. The singularity is not somewhere you can try to dodge. It is a moment every future heartbeat is stepping toward. All of this is hidden from us by the horizon. From our side, TON 618 remains a dark center surrounded by a bright disk. We cannot see the interior. No light from the region inside the horizon ever reaches us. No signal, no message, no photograph. Our entire picture of what happens past that boundary comes from our trust in general relativity and our willingness to let mathematics guide imagination, where observation cannot follow. So far, every test we can perform of those equations outside the horizon has supported them. That gives us confidence that the story they tell inside is at least close to right. It is worth pausing here on the scale of what we are talking about. TON 618 contains around 66 billion solar masses in its gravity well. Its horizon radius is hundreds of billions of kilometers. It sits roughly 10 billion light-years away in space and 10 billion years away in time. No spacecraft we will ever build is going there. No probe is falling in and sending back data. And yet, with equations written on paper and photons collected in telescopes, we can say meaningful things about the geometry of its horizon and the fate of anything that crosses it. There is a kind of quiet awe in that. We are small, temporary creatures, thinking about a region of space-time where the rules we know are pushed almost as far as they can go. The event horizon of TON 618 is both a physical boundary and a boundary of knowledge. On one side, we have data. On the other, we have theory, tested as far as we can test it and then extended into the dark. So far, we have stayed with the view from the outside and the general map of the inside. In the next step, we will turn this into a more personal thought experiment. We will imagine falling in, not just crossing the horizon, but continuing toward the singularity, feeling how the gentle tides at the boundary slowly grow into something lethal. That is the journey that awaits us next. Imagine, as a thought experiment, that you decide to fall into TON 618. You're not being yanked in by surprise. You are a volunteer. You know what the equations say. You understand that this is a one-way trip. You have instruments, clocks, cameras, and a mind that stubbornly wants to turn experience into understanding all the way down. That desire to understand is the last human thing you get to keep. Long before you reach the horizon, the universe behind you has already started to look strange. Light from distant galaxies is focused and distorted by the huge gravity of the black hole. The part of the sky near the hole is stretched into a bright, warped ring. The rest of the universe is squeezed into an ever smaller patch of your rear view. Signals you send outward take longer and longer to escape. Replies, if any, arrive more and more delayed and redshifted, yet locally your ship feels fine. Assume for a moment that you have already threaded your way through the dangerous glare of the accretion disk. You've avoided the jets, shielded yourself from most of the radiation, and now you are in a relatively empty region just outside the horizon. The black sphere ahead is not something you can see directly, because it is not a surface. It is simply the part of the sky where no light emerges. You fire your engines briefly to cancel as much sideways motion as possible, then you turn them off and let gravity take over. As you cross the horizon of TON 618, nothing in your cabin jolts. Your feet do not suddenly feel heavier than your head. Your instruments do not flash a warning that the universe has changed its mind. Your own clock ticks onward. From your perspective, the crossing is just another moment on the way down. If you did not know where the horizon was supposed to be, you would not be able to point to the instant you passed it. The real difference lies in the structure of your future. Outside the horizon, burning fuel in the right direction could in principle carry you back out into the wider universe. Inside, no amount of engine power can do that. Thrust merely changes how you fall, not whether you fall. Mathematically, the direction inward has become woven into the flow of time. Physically, every event that happens to you from now on sits on a path that ends at the singularity. At first, that singularity is far away in terms of the time on your ship. For an ultramassive black hole with the mass of TON 618, the proper time between crossing the horizon and reaching the singularity can be on the order of days. That number is fuzzy, because rotation and details of your trajectory matter, but the important part is this. You would not have seconds. You would have hours or more, enough time to run experiments, to watch instruments change, to feel tension grow. During the early part of the fall, tidal forces are gentle. Tidal force is the difference in gravity between one part of you and another. It is what lifts tides on Earth as the moon pulls a little harder on the near side of the oceans than on the far side. Near a small black hole, those differences become deadly quickly. Near a giant like TON 618, they start small at the horizon. The distance from your head to your feet is tiny compared to the radius of the hole, so the change in gravitational pull over that span is minor. You might feel lighter or heavier depending on how you orient yourself, but you would not be ripped apart. You could float in free fall, weightless in your cabin, watching space-time itself carry you inward. As you continue, the story changes slowly, then rapidly. The closer you get to the center, the more sharply gravity increases. Tidal forces strengthen. If you align your ship radially, with one end pointing toward the singularity and one away, the pull on the lower end grows stronger than the pull on the upper end. At the same time, gravity squeezes you sideways, because space is curving inward from all directions. This is the origin of the word spaghettification. You're stretched along the direction of fall and compressed in the perpendicular directions. At first, the effect is tiny. Slight differences in stress across your body. Instruments might pick up gradients in acceleration before you consciously feel anything. Then the effect climbs into scale after scale. At some depth, the tidal forces become strong enough to challenge the structural strength of your ship. Metal strains, bolts creak. Beams that were designed to handle ordinary stresses on Earth now carry loads they were never meant to face. If you had the misfortune to fall into a small stellar mass black hole, this threshold would happen outside or near the horizon. In TON 618, because the hole is so massive, much of that drama is postponed until you are deep inside. The next thresholds are more intimate. Bones, muscles, and connective tissue have limits. There is a point at which the difference in pull between your head and your feet exceeds what your skeleton can handle. Vertebrae strain and snap. Internal organs shift. Blood vessels stretch. The word spaghettification is cartoonish, but what it describes is not. It is a progressive failure of structure under a gravity gradient that grows without bound as you approach the singularity. Past that, the breakdown continues at smaller scales. The forces tear apart cells, then molecules, then atoms. Electrons are stripped from nuclei. Even composite particles would not survive the final approach in the idealized picture of a classical singularity. The curvature of space-time becomes so extreme that our present theories stop giving sensible answers. We can label that region with symbols and call it infinite, but what it feels like is simply this. There is no material object left to feel anything. From the perspective of a distant observer who somehow kept watching all of this, the story would never reach those final moments. They would see your descent slow and fade as you neared the horizon, then disappear into the background glare of the quasar. Your radio calls would drift lower and lower in frequency, taking longer and longer to arrive until they blended with the noise. They would never see you cross, let alone fall toward the center. From your perspective, the opposite is true. You never see yourself fade or freeze, you never watch your own signals die out. You live through each moment in sequence, all the way down, until tidal forces first threaten, then break you. You experience the inside of the horizon as a finite future, filled with real events measured by your own clock. The cruelty of an ultramassive black hole like TON 618 is not just in its power, it is in this schedule. A small hole kills quickly, a giant grants you time to understand what is happening while it happens, time to take measurements, time to think, and perhaps to regret. Time to feel your world shrink from the entire universe to a cabin, then to the space of your own body, then to nothing at all. And when you try to ask what lies beyond that nothing, you run into a different kind of limit. Our description of spaghettification and the long fall is based on general relativity, a theory that has passed every test we have thrown at it in regions we can observe. But as we approach the singularity itself, the equations predict infinities. Curvature goes to values that have no physical meaning. Densities become undefined. This is the universe telling us not that reality becomes infinite, but that our theory has been pushed past where it knows what it is talking about. In that sense, the endpoint of your fall into TON 618 is not just a physical boundary, it is an epistemic one, a place where our present understanding of space-time collapses, even as space-time itself continues to do whatever it actually does. To face that honestly, we have to step back from the personal thought experiment and look at the larger paradox that lurks behind every black hole. The question of what happens to information in a universe that seems to let matter and energy fall in, but never come back out. That is where the final part of our journey leads. We have followed our imaginary fall into TON 618, all the way down to the point where tidal forces crush anything made of matter. Yet even there, we are still playing on the surface of a deeper mystery. General relativity, the theory that has guided us so far, does not simply say that gravity becomes strong. It says something more radical. It says that if you keep following the equations all the way in, space-time itself reaches a point where its own description breaks. That point is what we call the singularity. Singularity sounds like a place, as if you could put a pin in a map. It is not really a place in that sense. In the mathematics of general relativity, it is a region where certain quantities that describe curvature grow without bound. The bending of space-time becomes infinite in finite time for anyone who crosses the horizon and keeps falling. Volume shrinks towards zero. Density goes the other way. The geometry that was smooth and continuous everywhere outside suddenly develops a kind of tear. Physically, infinities like this are red flags. When a theory predicts that some quantity blows up to infinity, it usually means the theory has been pushed beyond where it is valid. That is not uniquely true of gravity. It happens in simpler physics as well. Older models of atoms once predicted that electrons would spiral into the nucleus in no time, radiating energy without limit. Quantum mechanics arrived and replaced that picture with a better one. The infinities were a sign that the older model was incomplete, not that nature itself was misbehaving. Most physicists think the same way about black hole singularities. The problem is not that the universe literally produces a point of infinite density. The problem is that general relativity is a classical theory. It treats space-time as a smooth fabric and ignores the quantum graininess that seems to be present in matter and fields everywhere else. Near the centre of a black hole, where curvature becomes extreme and distances become tiny, it would be shocking if quantum effects did not become important. So the singularity is like a warning sticker on our equations. It says beyond this, your current understanding cannot be trusted. The trouble is that we do not yet have a full theory that combines quantum mechanics and gravity into a single consistent framework. We have candidates with different strengths and different weaknesses. Loop quantum gravity suggests that space-time itself may have a discrete structure at the smallest scales, with geometry built from tiny loops. String theory imagines fundamental objects as one-dimensional strings rather than point particles, and uses extra dimensions and rich mathematics to smooth out some of the infinities that plague classical gravity. In these and other approaches, there are hints that what we call a singularity might be replaced by something finite. Perhaps the collapse is halted when density reaches some enormous but not infinite value. Perhaps the interior of a black hole connects to another region of spacetime or even to another universe, in a way that we cannot interpret within classical thinking. Perhaps the endpoint of collapse is not a point, but a kind of exotic core where geometry is wildly curved but not truly singular. The key word is perhaps. Right now, all of these ideas live in the realm of theory, not confirmed fact. We cannot send instruments inside the horizon of TON 618 to measure space-time near the centre. We have to rely on mathematical consistency and on indirect clues from phenomena we can observe, such as gravitational waves from black hole mergers and the fine details of radiation near horizons. Those clues are slowly accumulating, but they have not yet forced us to choose one clear picture of what replaces the singularity. This is part of what makes TON 618 so fascinating. A singularity inside a stellar mass black hole is already a challenge for physics. A singularity inside an ultramassive black hole stretches that challenge to its most extreme. The curvature predicted by classical relativity near the centre is beyond any scale we can test. The total mass involved is astronomical in every sense. If quantum gravity does something clever to avoid infinity anywhere, it almost certainly has to do that inside objects like this. There is also a deeper conceptual issue wrapped around singularities. They are places where predictability fails. One of the central virtues of general relativity is that, given initial conditions on some slice of space-time, you can in principle evolve the equations forward and know what happens next everywhere. A singularity is a place where that evolution cannot continue. The path of events ends. For an infalling observer, that is literally true. Their world line stops. For the universe as a whole, it means there are regions where the theory cannot say what lies beyond. In the case of TON 618, that failure hides behind the horizon. Whatever happens at or near the singularity does not leak out to affect the wider universe in any direct way, at least according to classical relativity. From the outside, the black hole looks fully described by a few parameters: mass, spin, and electric charge. Everything else about the matter that fell in, all its complex structure and history, drops out of the external description. This is sometimes called the no-hair property. Black holes, in this simple picture, are bald. That simplicity is unsettling. Our everyday experience tells us that the world keeps track of details. Smash two snowflakes together, and the air around them remembers something about their shapes in the pattern of water droplets and airflow. Let two books fall into a fire, and the ash and smoke still encode some information, at least in principle, about which letters were on the pages. If a black hole really reduced everything to just a few parameters, and then hid a singularity where predictability dies, it would seem to break the habit the universe has of preserving information in some form. This is where the story begins to merge with what is often called the information paradox. On the one hand, classical general relativity says matter and information can fall behind the horizon and end in a singularity, gone from the world outside forever. On the other hand, quantum mechanics insists that information about physical states cannot simply vanish. The evolution of a quantum system is supposed to be reversible at a fundamental level. The two stories clash. To resolve that clash, many physicists suspect that the singularity in the horizon must be modified in a full theory in ways that restore information, even if the restoration is subtle and unimaginably hard to decode. Perhaps the interior is not really a one-way trash bin. Perhaps the horizon is more than an empty boundary and has its own microscopic structure. Perhaps the classical picture of a smooth space-time with a central point of infinite curvature is only the large-scale shadow of something more intricate. For now, faced with TON 618, the honest statement is that we are running at the edge of what we know. We can describe the plunge from the horizon inward, as long as tidal forces are small and curvature is moderate. We can follow the equations until they start predicting nonsense. We can gesture at quantum corrections and new physics that we believe must come in. We can sketch possible scenarios where singularities are replaced by bounces or resolved cores. But we cannot yet say which of these is the way the real universe behaves inside this monster. In that sense, TON 618 is not just a physical object. It is a boundary marker between two eras of understanding. Outside its horizon, gravity is a solved problem in practical terms. We can track orbits, model disks, predict lensing, and match observations to theory with impressive accuracy. Inside, toward the singularity, gravity becomes a question that future physics has to answer. In the final part of this journey, we will step back from the specific geometry of TON 618 and look at the wider puzzle that black holes pose for fundamental laws. Not only what happens at the center, but what happens to information itself, and what that might tell us about the next layer of reality beyond the theories we have now. Stand outside TON 618 one last time in your mind. You see the blazing disk, the jets that may have once carved through space, the calm, dark circle at the center. From the outside, it all looks almost simple. A few numbers describe it. Mass, spin, maybe charge if any is left. Everything that ever fell in has been washed clean from the surface story. But that simplicity hides a question so sharp that it cuts right into the foundations of physics. What really happens to information in a universe that allows black holes like this? On one side of the argument stands classical gravity. In that picture, matter falls through the disk, crosses the horizon, and heads for the singularity. Once inside, nothing ever comes back out. Whatever pattern the matter carried, whatever arrangement of particles and fields, is lost to the outside world. From far away, the black hole settles down to a smooth, featureless state. Only its mass, spin, and charge remain visible in the gravitational and electromagnetic fields it produces. On the other side stands quantum mechanics, which has been annoyingly consistent about one thing. Information about the exact quantum state of a system does not simply vanish. It can spread, scramble, and hide in correlations so subtle that no practical observer could ever reconstruct it. But at the deepest level, the evolution is reversible. If you knew the exact final state and the exact rules, you could in principle run the clock backward and recover the past. Put those two stories together around an object like TON 618, and they collide. Imagine throwing in a carefully prepared collection of particles with a pattern that encodes a message. Classical gravity says the message is gone from the outside universe once it crosses the horizon. Quantum mechanics says that cannot happen. The universe is not supposed to throw away bits. Somewhere, somehow, the information about what fell in must be preserved. Stephen Hawking raised the stakes when he showed that black holes are not perfectly black, once quantum effects near the horizon are taken into account. In his calculation, pairs of particles can pop into existence near the horizon, with one falling in and the other escaping as radiation. To a distant observer, the black hole slowly loses mass and shrinks while emitting a faint glow. This Hawking radiation has a very specific temperature and spectrum that, in the simplest version, depends only on the mass and spin of the hole, not on the details of what fell in. If that radiation is truly featureless, then as the black hole evaporates away over immense spans of time, all the detailed information about what formed it and what fed it would be washed out into a smooth bath of particles that reveals nothing. At the end, there would be only radiation and empty space. The message you threw in would be gone, not just practically, but fundamentally. That is the heart of the information paradox. For Ton 618, the timescale of evaporation is so enormous that it might as well be forever compared to the current age of the universe. But the paradox is not about clocks. It is about whether the laws of physics are consistent with themselves. If information can be destroyed in principle inside objects like this, then quantum mechanics as we know it would have to be revised. If information is preserved, then our simple classical picture of horizons and singularities must be missing important structure. Over the past few decades, many possible resolutions have been proposed, like trial sketches of a painting we have not finished. One idea is that Hawking radiation is not truly featureless at all. Perhaps it carries extremely delicate correlations that encode the information about what fell in. To any practical observer, the radiation would look random. In principle, however, the full pattern of emissions across the whole lifetime of the black hole could be rich enough to reconstruct everything. Another idea comes from the holographic principle. It suggests that the total information content of a region of space is proportional not to its volume but to the area of its boundary. In the black hole context, this leads to the thought that all the information about the interior might be stored in degrees of freedom living effectively on the horizon itself, like bits on a cosmic screen. In that view, the horizon is no longer just an empty boundary. It is an active surface where information is shuffled and eventually re-expressed in the outgoing radiation. There are even more exotic pictures where entanglement and geometry are deeply linked. In some of these, connections that look like wormholes in space-time may be another way of talking about quantum entanglement between distant systems. If that is true, the interior of a black hole and the radiation far away might be joined in ways that preserve information, without allowing any simple signal to travel faster than light or escape from behind the horizon. None of this is settled. Different approaches struggle with different aspects of the paradox. Some cope well with information, but seem to require dramatic changes to physics near the horizon, such as the appearance of a violent boundary layer where an infalling observer would be destroyed. Others keep the horizon gentle but rely on subtler quantum structures that are hard to visualize. Many physicists suspect that the final answer will look unfamiliar from the perspective of both classical relativity and simple quantum mechanics. What does this have to do with Ton 618 in particular? In one sense, nothing. The paradox would exist even for a small black hole. In another sense, everything. An ultramassive black hole is an extreme case. It is a vast reservoir of entropy and information in the language of statistical physics. Whatever the correct picture is, it has to work not just for tiny horizons, but for giants that contain the mass of billions of suns. There is a practical side to this search for understanding as well. We are no longer limited to pure theory. Observations of merging black holes through gravitational waves are giving us new tests of how horizons behave. The images of shadow-like regions around supermassive black holes in nearby galaxies show us light bending near the brink. Future missions may measure gravitational waves from even more massive mergers, or see subtle imprints of strong gravity in the way matter moves around black holes like the one in Ton 618. These observations will not show us the interior directly, but they can challenge or support different ideas about how closely real black holes follow the simplest solutions of general relativity. Tiny deviations might be the first hints that there is more going on at horizons than the classical picture suggests. At the same time, work in quantum information theory is changing how we think about the paradox itself. Ideas from error-correcting codes, entanglement structure, and complexity are being used to model how information spreads and hides in systems that look, from the outside, almost thermal. Black holes, once seen mainly as astrophysical curiosities, have become central players in conversations about the nature of reality, from the microscopic to the cosmic. Standing in the shadow of Ton 618, all of this becomes more than an abstract puzzle. This single object embodies the tension. It is both simple and complex. Simple in its external description, complex in what it does to space, time, and information. It sits in our universe as a reminder that the theories we have are powerful enough to predict monsters like this, yet incomplete enough that we cannot say exactly what happens to every bit of information they swallow. There is a quiet irony here. Black holes are often described as the places where the universe hides things from us. Yet by forcing our theories into conflict, they are also the places where the universe reveals that we do not yet know enough. They mark the spots on the cosmic map where the words "here be dragons" are not about mythical creatures, but about our own ignorance. One day, perhaps, a deeper theory of quantum gravity will make objects like Ton 618 feel as familiar as planets and stars do now. The singularity may be replaced by a well-understood core. The horizon may be revealed as a dynamic, information-rich surface. The information paradox may become a textbook example of how apparent contradictions can vanish when you have the right language. Until then, Ton 618 stands at the edge of what we can honestly claim to understand, a lighthouse that should not exist, burning in the dark of a younger universe, powered by an engine we mostly grasp and hiding an interior we mostly do not. The universe is under no obligation to explain itself. We are under no obligation to stop asking. And that difference between a silent cosmos and a species that insists on listening anyway might be the most important thing this monster has helped us see.